Okay guys, I'm going to try and pick up where we left off yesterday. I know yesterday we went over the numbers and we talked about oil flow through the base valve and the mid valve, or I was referring to them as the active valve and the passive valve. So we got our volumes of oil and we got our ratio, and today we're just going to take a further look into piston port geometry and pressures inside the shock or the fork, and explain how that affects the ride of the bike. So yeah, picking up from where we left off yesterday, so I'm going to pick on the shock and talk about these three pistons that I've personally ridden on. I've gone through and taken some quick measurements, and we have 264mm squared on the alloy piston on port entrance, 225mm squared on the WP, and 208mm squared on the shower. And I can tell you from personal experience that the alloy piston certainly rode the stiffest, had the slowest rebound, then the stock, and then the shower, which rides the softest, has the quickest rebound. And we're sort of going to get into why that might be the case. But first, I mean, anyone that's watching this video probably has a fair idea on how a shock absorber works, and I know it's possibly getting into semantics, but I think we sort of need to go over that and establish what's really going on inside the shock, so we can get an understanding of why these pistons behave the way they do. So we all know that during compression the shock shaft enters the body, and we quite often refer to it as oil flowing through the piston, but in reality it's a case of the piston flowing through the oil. And we all know that the space that's taken up by the shock shaft needs to be compensated for, and it's that volume of oil which passes through the passive valve. In the case of this shock, we measured it out at 36mm. So we understand that happens, but I think it's a good idea to sort of try and establish what happens with these three different pistons. Okay, so we're going to have a really good look at these pistons again. I know I've just given you the measurements on each one. So I want to use an analogy of cycling a mountain bike into a strong headwind. You're upright, you've got a big jacket on, you've got a lot of wind drag. So that's what happens when you use a restrictive piston. It's the same thing. There's a lot of pressure in front of the piston and less pressure behind it. That pressure in front of the piston's acting on the passive valve. So that's what goes on with the restrictive piston. In the case of the high flow piston, it's kind of like you're on your road cycle, you've got your lycra on, you're tucked up in the aerodynamic position. So the result of that is less pressure in front, more pressure behind. The consequence of this in the case of the shock absorber is there's now less pressure acting on our compression adjuster shim stack. So that has an impact on the flow, because unfortunately the only way oil gets through this is if it's driven through that. And it's quite common for a lot of other tuners. They say, oh, this volume of oil that we've measured, the 36mm, that's displaced by the shock shaft. Well, the problem with that is if you're trying to push that oil through the passive valve using the shock shaft, the only way you can do that is to push it off the shock shaft, back through the main piston, up through the oil in the compression chamber, and out the passive valve. So it stands to reason that that's, it's an inefficient method of pushing that oil out. In reality, what happens is you end up with a hydraulic lock under the piston. So hence this high flow piston, it feels stiffer and it has a slower rebound. The reason it has a slower rebound is we have a pressure spike in the rebound chamber. So the rebound chamber pressure increases, the compression chamber pressure is now lower than it would be, say, with the more restrictive piston. We have less pressure working on our passive valve, which then drives less oil out the compression adjuster. The result is a shock that rides firmer, even though on paper it should be softer. So like I was just saying, We'd think that the alloy piston, the machined alloy piston, would be the softest, just based on the fact that it's going to flow the most oil. But like I just explained, because it has less pressure in front of it, it actually drives less oil through that passive valve and ends up with that higher pressure in the rebound chamber. It needs to be said that when I tried these three pistons, I used the exact same compression stacks, the exact same rebound stacks, the same stack on the compression adjuster, same spring rates and same oil, same nitrogen pressure. So there was no variance in anything other than piston port geometry. And like I was saying just before, it's because we need to drive oil out this passive valve that's what causes these pressure spikes in the rebound chamber when you have too much flow through the active valve. So the same thing can happen on your fork. You know, it's quite common to see guys use excessive amounts of float. Like back in the day, it was all check plates, 1/2 mil float, plenty of bleed, all that sort of stuff, and it was quite common for people to complain about harsh forks or heaps of deflection. And the reason was you were never creating enough pressure in front of the piston to drive the oil through the base valve. Unfortunately, you can't expect to drive the oil through the passive valve off the damper rod or the shock shaft. The reason for that is that to do so, you would need to flow the oil against the oil that's already flowing through our active valve. You need to flow it back in the opposite direction and out the passive valve. So the idea is to meter the oil appropriately. So we want to limit the amount of oil flow through our active valve so it's balanced with our passive valve. Now, the problem with this is the only way we could do it with a high flow piston is we keep stacking it up. We just need to add heaps of shims, and that's going to delay the opening time of that valve. So hence KYB Showa, these guys seem to be pretty onto it. They know you need to produce sufficient pressure in front of the piston to work on the compression adjuster stack. And it's the same case with the fork. Like we've seen now, they've all moved to trampoline style valves. We usually have a plate that limits the amount of flex on these shims, and we also have a limited amount of oil flow into the piston as well. In the case of my bike, so just changing the backing plate from 14mm to 16mm, that has a sufficient impact to sort of limit the shim flex, which then limits the flow through that valve and then subsequently puts more pressure on the passive valve. And this is the thing, so it's all to do with pressure. Like it doesn't matter how we change things, what we end up essentially doing is altering the pressure. That we alter the pressure in the compression chamber, we alter the pressure in the rebound chamber. You know, you go 3 clicks, 4 clicks out on rebound, you end up with less pressure in the compression chamber, more pressure in the rebound chamber. You go 4 clicks out on the compression adjuster, you end up with less pressure in the compression chamber, less pressure in the rebound chamber. So it's all manipulating those pressures to get the desired ride quality. And the thing is, there's this misconception about these high flow pistons. They do ride stiffer just because of how they affect the pressure. You need to drive that oil through that passive valve to get a sufficient ride quality. And if you don't, you end up choking the passive valve if you can't create that pressure. If you're trying to use that damper rod, if you're trying to use that shock shaft, which is working against the flowing oil through the active valve, that's just going to cause a big pressure spike, and it's the quickest way to make a harsh ride. You would definitely see firmer stacks both on the main piston and the compression adjuster these days, as everyone's moving towards this more linear damping profile. I mean, there's still exceptions to the rule. KTM continue to muck around with high flow pistons. I see in the latest 23 bike, they now use a smaller 38mm rebound shim, and again they're chasing more flow through that active piston. The consequence though is a bike that sort of has a slower rebound, and then they try and combat that with their aftermarket shock like the tracks. But if only they did what KYB did and realised that they're causing this pressure spike in the bottom of the shock in the rebound chamber, Might improve the ride quality through the works for some of the boys. So how do you diagnose a shock that's poorly balanced? I think that's the next thing I'm going to talk about, shock or fork. So a shock, the biggest telltale sign that I quickly learnt was that you end up with a shock that seems to hang up on square edge stuff. So might be a case of acceleration shock, be coming out of a corner and there's just a delay for the wheel to ride over the square edge bump. And in the case of a fork, it's the same thing. When you're coming into the corner, you got all that those braking bumps, and you get a wheel that sort of wants to deflect. It just doesn't want to roll over the bump. And the reason we're seeing that is because of that delayed rebound from the pressure spike in the rebound chamber. So it slows down the rebound, the initial rebound, and unfortunately your wheel doesn't want to travel over that object until the rebound stroke has started. So that's the quickest way to diagnose that you just have that imbalance between your active valve and your passive valve. And if you've got like a stock KTM, no, only thing you can really do if you're going to continue using the stock piston is you just need to go lighter on your compression adjuster stack, and that's what KTM did for many years. You know, we saw these really light stacks on the compression adjuster stacks. These days they've sort of turned it around, they've beefed up the compression adjuster stack, but they've really beefed up the main piston as well. In the case of a fork, you've got two options when you get to this point. You've got that deflecting fork. You notice it mostly going down hills. Like I say, it just doesn't want to roll over that those braking bumps coming into the entrance of a turn. You've got two options basically. You lighten the base valve setting because we know we're not producing sufficient pressure to drive the wheel through the base valve, so we can lighten the base valve setting. That means we need less pressure to drive the same amount of flow. Or you can stiffen up your active valve. So you can either limit the shim deflection, change the piston, limit the bleeds, couple clicks in on the rebound, those sorts of things. So what we need to do is we either need to reduce the amount of pressure to drive flow through this, or we need to produce more pressure in front of it to drive the flow through this. So yeah, that's something you can do. So I think this it's all pretty quick, but it's a basic idea of what's going on there with the pressures and stuff like that. I'm going to try and include a link from Penske, which I think is really valuable, where they talk about pressure balancing. Those guys have been doing it for a long time. Again, it's something you possibly want to do if you're really into the suspension stuff, is probably look outside the scope of motocross, because there's a lot of information out there, and quite often I get told, oh, this is motocross, it's different. Well, it's not different. These shocks all function the same. They all need to maintain a good pressure balance. Oils flows in the same principles. So yeah, that's another thing to look into, I think. But I'm going to wrap it up here, and come back with another one sometime soon.